Hello, my name is Andrew Arma, and this is Lab 5 for Physics 2211, Intro to Physics 2. In this lab, we investigated the effects of electromagnetic induction on magnetic dipoles in conducting loops. This was done by dropping a magnet through a conducting tube and seeing how its motion is effective. This lab relies on multiple theories of electromagnetism. The first thing that is needed is a definition of a magnetic field. The direction of a magnetic field can be found by taking the cross product of the magnetic moment and the relative position vector. The magnitude of the field strength can be calculated using the Biot-Savart law as shown. Magnetic flux is the amount and direction of magnetic field lines normal to a surface, represented by the dot product of the magnetic field and the line normal to the surface. Finally, Faraday's law of induction states that when a magnetic flux varies with time, an electric field is induced. If this electric field is induced within a conducting material, a current is created with a voltage equal to the magnitude of the change in flux. This current creates a magnetic field that resists the change in flux. This causes an object, or a magnet, dropped through a conducting tube to slow down. The experiment was performed by dropping a bar magnet through a tube of aluminum and seeing how it falls. The magnet fell more slowly in the tube than it did when it dropped normally, which means the current running through the tube was exerting a magnetic field on the bar. The experiment was modeled using GlowScript. The theoretical concepts above were used to calculate the magnitude and direction of the force. Since there is no formula for the force of a magnetic field on a dipole, or bar magnet, Newton's third law had to be used. The force of the bar magnet on the conducting tube is equal and opposite to the force of the conducting loop on the bar magnet. From this, we can determine the net force on the magnet, which includes gravity, and from there, model its motion and velocity. If the resistance of the conducting tube were almost zero, the voltage and current through the tube would be larger, which would create a larger magnetic field. This would slow down the magnet further. The closer the resistance is to zero, the more the magnet's velocity would slow down. However, the magnetic force can never be greater than the gravitational force for an extended period of time. This is because if the magnet stopped moving, or the velocity became zero, no more current would be induced, which would reduce the magnetic force to zero. If holes or slots were cut into the conducting tube, the ring's current would be decreased because charges would have to move further to travel in a loop, increasing the resistance. This would make the magnet slow down less.